Oh, that's good.
I'm actually not. Anything else, so.
Oh, really?
I use the vector field.
I know, me too.
I want to call your attention to the fact that we have to leave this room because it's too big and bigger classes needed. So effective next lecture, which is on Wednesday, September 1st, we'll be moving to 325 LeConte. So please don't forget that. All right, last time I was telling you about Hermitian operators. I reviewed here the definition of a Hermitian operator, which actually comes in two different forms, rather easily equivalent. And I just want to mention a very simple but important theorem that occurs in quantum mechanics, which is that if you have two Hermitian operators, then the product of those Hermitian operators is Hermitian if and only if they commute. Proof is so trivial that I won't go over it in class, but it is something that will occur many times in the course. Now, what I'd like to start addressing today, first of all, is the subject of eigenvectors and eigenvalues, or eigenkets and eigenvalues. Let's suppose we have an operator A, not necessarily Hermitian, acting on some ket space, and we have some non-zero ket U, take it to be non-zero, such that when you let A act on U, it just multiplies U by a number, lowercase a, which in general is a complex number. Here, capital A is the operator, and lowercase a is what we call the eigenvalue, as I guess you all know. And likewise, the ket U here, we'll call this the eigenket, or sometimes eigenfunctions if we're talking about wave functions, or eigenvectors. Anyway, that's the eigenket and the eigenvalue. The eigenvalue, as I mentioned, in general is a complex number. It depends on the operator A. Now, the situation regarding, or the theory regarding eigenvalues and eigenkets is considerably simpler in a finite dimensional ket space than it is in an infinite dimensional one. So I'm going to begin by telling you about finite dimensional spaces, but I'll make a few comments as we go along about how the situation is different in infinite dimensions. Here's the first thing to notice is that if you have a ket U, an eigenket, now it's supposed to be non-zero because if it were equal to 0, this equation just says 0 equals 0, and it's not very interesting. So we exclude the 0 case. So if U is a non-zero ket, then you can think of it as a vector that sticks off somewhere like this in the space in question. Here's the vector U, or the ket U. It's obvious from the eigenket eigenvalue equation, however, that if you multiply U by any complex constant, you get another eigenket. So this equation does not uniquely determine the eigenket, only to within a multiplicative constant. Or to say it another way, if I take this non-zero ket U and I multiply it by any factor I want, it could be a negative factor as well. And since these are complex vector spaces, it could be really complex numbers, including phases and so on. But in any case, the result is what you get is, from a given non-zero ket, you can construct a whole one-dimensional subspace of eigenkets. You could call this an eigenray if you want. In some sense, this equation really determines an eigenray rather than a single eigenvector. Now, it may happen that there is, in addition to this vector U, this ket U, it may happen that there's another vector, or ket, which is linearly independent of the first one, which is also an eigenket with the same eigenvalue. Let's call this B, let's say. AB is equal to lowercase ab. The point is the a's here are the same, but the b's here are different. And let's suppose that B is linearly independent of U, so that it sticks off in some direction like this. Here's the B. then it becomes apparent that any linear combination of the U and the V is also an eigenket. And so the space of eigenkets, you see, becomes a two-dimensional vector space like this. Under these circumstances, it becomes appropriate to speak of an eigenspace. And that's what we'll do. We'll call this the eigenspace. I'll call this E sub A, script E sub A. I'm generally using the notation script E here for the entire ket space, the entire vector space. So with an A subscript on it, it stands for the eigenspace corresponding to eigenvalue A of a given operator A like this. And the result of this is that we get a geometrical interpretation of this eigenvalue-eigenket problem, which is that if you have an operator A, it corresponds to certain privileged subspaces of the ket space. In general, we can think of, if I think of two of them, just try to draw a picture of it. If I've got two spaces, here might be one, and then here might be another one going off like this. Well, I've drawn one of them to be two-dimensional, one to be one-dimensional. Let's say this is E1 and this is E2, are two different ket spaces corresponding to eigenvalues A1 and A2. You can imagine it looking something like that. All right. Now, as you probably know, if there is more than one linearly independent eigenket, then we say that there's a degeneracy. And the number of linearly independent eigenkets that correspond to a given eigenvalue is something we'll call the order of the degeneracy. So the way I drew it here, the order is 2 because it spans a two-dimensional subspace. The order of the degeneracy is just the dimension of the eigenspace. If the eigenspace is one-dimensional, like I drew here for this E2, then we say it's non-degenerate, which means that it doesn't mean the eigenket is unique, but it's unique to within a single multiplicative constant. All right, so as we'll say here, the dimensionality of the eigenspace En is what we'll call the order of the degeneracy. So the order of the degeneracy is always 1, but it could be greater than 1. All right. Another thing that comes out of this is that given operator A is associated with a collection of numbers, generally complex numbers, which are the possible eigenvalues of A. That's got a terminology. It's called the spectrum of the operator A. So the spectrum of A is just the set of eigenvalues A n of A. That's all it is. This is the spectrum of our operator A. And it's usually viewed as being a subset of the complex plane. So if it's a complex eigenvalue plane, really. So if I have the real A and imaginary part of A as being give us the complex plane for the eigenvalue, then in general the spectrum, and I mentioned a moment ago that I'm describing the situation in a finite number of dimensions, first for simplicity. And if we're in a finite number of dimensions, the spectrum consists of a discrete set of points which can be distributed here and there in a complex plane. That's the spectrum of the operator. All right. That's just some terminology mostly. Let me give you some examples of spectra of operators coming from quantum mechanics. Let's first of all talk about the harmonic oscillator Hamiltonian. The harmonic oscillator Hamiltonian. So let's write H x on UN gives us E n UN. And as you all know, the energy eigenvalues are equal to n plus a half h bar omega. And so the spectrum, we have to look in the complex energy plane. There's real energy, imaginary energy. The spectrum consists of points first 1/2, then 3/2, 5/2, 7/2, and so on. As you see, it's a discrete spectrum, and it's on the real axis. Here's another example. Let's take the free particle, h equals p squared over 2m. And then here's what the spectrum looks like, real energy, imaginary energy. In this case, there are eigenfunctions for all non-negative values of the energy. So the spectrum consists of the entire real axis like this. Try to draw it heavy. The entire positive real axis, not negative. This is an example of what's called a continuous spectrum because it's not discrete points. continuous spectrum only arises in infinite dimensions, and I'll say more about it a little later, but right now just giving you a preview of some of the things that can happen. Here's another example. Let's take the hydrogen atom, Hermitian. Again, we talk about the energy spectrum, so real energy and imaginary energy. In the case of the hydrogen atom, you know the ground state, everyone knows it's minus 13.6 electron volts, so there it is, there's the ground state and the negative energy. And then there are other bound states of negative energy, and they pile up. They have an accumulation point at E equals 0. There's actually an infinite number of them that accumulate there. And then, they don't actually emphasize this enough, but for positive energy, there's a continuous spectrum. The hydrogen atom possesses a continuous energy spectrum for positive energy, which is similar to the case of the free particle as far as the spectrum is concerned. Anyway, that's the hydrogen atom. This is a mixture of a discrete and a continuous spectrum, as you can see. And then finally, let me just mention the case of a unitary operator. Unitary operator is one whose inverse is equal to its Hermitian conjugate, so this is unitary. And I'll write the real and imaginary parts here for the eigenvalues. It turns out the eigenvalues of unitary operators are always phase factors, and thus they lie on the unit circle in the complex plane. And if we are in a finite dimensional space, there's only a finite number of them, so they're just going to be discrete points which sit on the unit circle. They don't have to be evenly spaced or anything. They can be anywhere on the unit circle like this. So these are examples of what's meant by the spectrum of an operator, and you see in general they have to be viewed as in the complex plane. You see this from unitary operators. All right. Now, I think what I'm going to do is go over here and for the next phase of this. So that's the concept of the spectrum. Now, the whole subject of eigenvalues and eigenkets simplifies quite a lot in the case of the special case of Hermitian operators. And we say it's Hermitian. In fact, finding eigenkets and eigenvalues of arbitrary operators is a rather ugly process, and fortunately we don't have to do it very often in quantum mechanics. But in the case of there's Hermitian, there's a number of simplifications which I'll list here. The first one is, so here we want to think of A acting on U is equal to AU. The first one is that the eigenvalue A is real. You can see this in the case of the Hamiltonians, all of which had spectra that lie completely on the real axis because the Hamiltonians are Hermitian, but the unitary operator has eigenvalues in the complex plane. Anyway, for Hermitian operators, they're real. The proof of this is elementary. All we need to do is to take the eigenvalue equation and multiply on the left by the bra U, like this. So I'll multiply both sides. And so what we get is the matrix element AUA is equal to the eigenvalue A times the scalar product UU. And then we take this equation and we apply the Hermitian conjugate to both sides. The left-hand side turns into itself AUA. If A were not Hermitian, you get a dagger in the middle, but because it's Hermitian, it doesn't, so you get the same thing. That's what's special here. And on the right-hand side, you get A star times UU. And so the left-hand sides are equal, so the right-hand sides are equal too. And we're assuming that the eigenket is non-zero, because that's what we mean by eigenkets. So this scalar product UU is non-zero, so the result is that this implies that A is equal to A star. You've probably seen this proof before. It's a very simple proof. All right. The second thing to say is that the eigenspaces are orthogonal. And so the picture that I drew, if it's still there, up at the top of the board right there, is actually not a very accurate picture. Not for the case of a Hermitian operator. In the case of a Hermitian operator, I ought to draw it like this. So here's one eigenspace, let's call it E1, corresponding to an eigenvalue, let's say A1. And then here's another one, let's call it E2, corresponding to an eigenvalue A2. And these are orthogonal, so they're actually perpendicular to it. just like this. So if an ordinary operator, any old operator, corresponds to certain privileged subspaces of the Ket space, in the case of Hermitian operator, these are actually orthogonal subspaces. Now, to say these spaces are orthogonal means that any vector in one space, and any vector in one of these spaces, is orthogonal to any vector in the other space. I've drawn this so that the E1 is two-dimensional, so it's a twofold degeneracy, and E1 is non-degenerate, but the same picture applies in any case of any degeneracy. The proof of this is also quite simple. It works like this. Let me take, let's say that AX on U1 and gives me U1 all over again multiplied by an eigenvalue of A1, which I'll write out to the right now instead of the left. It doesn't matter which way I write it because it's multiplying a number times a vector. And then let's say there was a second vector U2, which is equal to U2 times A2. So these are two different eigenkets and possibly two different eigenvalues. Now let's take the first equation and multiply on the left by the bra U1. Excuse me, by the bra U2 on both sides. And then the second equation multiplied by the bra U1 on both sides. So we get this. And then let's take the second equation and apply a dagger to it. So we reverse things, U2A, U1. I don't dagger A because it's Hermitian. And then over here I get U2 scalar product U1 times A2 times A2, because we've learned earlier that the A's are real, so I don't have to complex conjugate the A's. But now you see, if we compare the first and the third equations, the left-hand sides are equal. And so the right-hand sides of the first and third equations have to be equal also. The scalar product is the same, so this implies that A1 minus A2 times the scalar product of U1, U2 is equal to 0. And so either the two eigenvalues are the same, or else the scalar product is 0. Which is clear on this picture here. Because if the two eigenvalues are different, so they belong to different spaces, then the vectors are orthogonal, just like I drew it here. On the other hand, if the two A's are equal, then there's nothing can be said about the scalar product. They're not necessarily orthogonal, and that's clear too, because if I've got two vectors inside space E1, they certainly don't have to be orthogonal to each other. Of course, I can choose them to be orthogonal if I want to. This is related to the fact that a Hermitian operator on a finite-dimensional space always possesses an orthonormal eigenbasis, which is something I'll come to in a little while. But you don't have to choose them orthogonal inside one of these eigenspaces if you don't want to. Okay. All right. By the way, eigenvectors are not unique. I mentioned that already because if just in the case of a single eigenvector, you can multiply it by any non-zero scale factor. Of course, normally in quantum mechanics, we usually normalize them to make them have a unit norm. But even then, that leaves the phase factor indeterminate. So even with that convention, you still got an arbitrary phase. If there's a degeneracy, it's worse than that because you see it's clear from this picture that you can rotate this any way you want. There's a huge number of ways of choosing orthonormal eigenvectors inside this two-dimensional space, or any space with a degeneracy of higher than 1. All right. Now, there are further simplifications in the case of Hermitian operators. And let me illustrate them by going back to this picture here for Hermitian operators. In fact, since I'm now talking about Hermitian operators, let me erase some of the rest of the stuff here which apply to other cases that I don't care about anymore. Let's get rid of that. All right, so let's talk about the case of Hermitian operators. We have two spaces here. The way I drew it, you're probably imagining this is a three-dimensional space, so it's broken up into 2D plus 1D. You can see that here. The question is, what would happen if this were in 4D? Suppose I had an operator that had the twofold degeneracy for one eigenvalue, a one-fold degeneracy for another eigenvalue. It acted on a four-dimensional space, but there weren't any more eigenvalues. Well, it would be like there weren't enough dimensions here to fill up the space. Okay, well this leads me to a concept now. I want to tell you about the concept of the direct sum of two subspaces. The direct sum, which I'll denote by, in this case, for this drawing, let's talk about the direct sum of these two subspaces, E1 and E2. What this means is the direct sum of these two subspaces is just the set of all vectors you can get by making linear combinations of vectors that come from either one space or the other space. So in this picture here, it's a three-dimensional space, you can see. Another way of saying it is that if I choose a basis in E1 and then another basis in E2, and I just throw these basis vectors together, in this case it would give me three basis vectors, and then consider the span of that, that's what we mean by the direct sum. So the result of this is that the dimension of the direct sum of these two spaces, E1 plus E2, is going to be equal to the dimension of E1 plus the dimension of E2. Dimensions add and they're taking a direct sum. This is just the meaning of the direct sum. Now, if we have an operator and we consider its eigenspaces, and then we take the direct sums of all of the eigenspaces, the question is, does that fill up the whole space? Like I said a minute ago, maybe this picture here is in 4D space, so we've got a two-dimensional subspace and a one-dimensional subspace, but it doesn't add up to 4. What happens then? And if that happens, then we say that the operator is not complete. So the completeness means to say that the eigenspaces fill up the whole space. Well, now there's a nice result about Hermitian operators, which is that they are complete. At least this is true in finite dimensions. They're always complete. This is not true for non-Hermitian operators, and it's one of the great advantages of Hermitian operators. It simplifies a whole lot of things. In finite dimensions, Hermitian operators are always complete. So it wouldn't happen in finite dimensions, namely 4, that you'd ever get 2 plus 1 equals 3, but missing some dimensions. It wouldn't happen, at least not for Hermitian operators. In infinite dimensions, it turns out this is not necessarily true, that there are Hermitian operators that are not complete. By the way, I don't know if I mentioned this last time, but in the mathematical literature especially, you hear the term self-adjoint. They're not, if you're a purist about this, they aren't exactly the same. They depend on domains of definition and stuff like that. I will never use the word self-adjoint, but if you see it, I think as a first pass in practical applications in quantum mechanics, you can regard them as being equivalent because they are for most applications. In any case, in infinite dimensions, there's a difference between, in infinite dimensions, a Hermitian operator is not necessarily complete. And so what we do is introduce a new definition, which is that of an observable. An observable is an operator, is an operator which is Hermitian and complete. It's not necessary to add the second part if you're in finite dimensions. In infinite dimensions, you should do this. Now, the reason this name is given has to do with the physical interpretation of quantum mechanics, in which one of the postulates of quantum mechanics is that if you make a measurement of a physical observable, is that the possible outcomes are the eigenvalues of the corresponding operators. And if the operator were not complete, and the operator is supposed to be Hermitian, and if the operator were not complete, then it would mean that if you added up the probabilities of all the possible answers you could get on making a measurement on ensemble systems, you could get an answer which was less than 1, because there would be some part of some vector that could stick off in these extra dimensions. This is absurd. It violates the physical principles of quantum mechanics. And this is why in quantum mechanics we deal not only with Hermitian operators, but actually with observables. These are the only ones we deal with, really. All right. Now, one of the consequences of going back to this picture here, one of the consequences which is fairly obvious from a picture like this, is that an observable, or any Hermitian operator in a finite dimensional space, let's talk about finite dimensions now, is that any Hermitian operator on a finite dimensional space possesses what we call an orthonormal eigenbasis. An eigenbasis just means, well, a basis means a set of vectors that span in space. And an eigenbasis means that there should be eigenvectors as well of a given operator. Well, it's clear this is true because if there's, all you have to do, since these different eigenspaces are orthogonal to one another, all you have to do is just choose an orthonormal basis in each of the eigenspaces. And then the collection of all of those becomes an orthonormal eigenbasis for the whole space. Here's some notation for this, talking about orthonormal eigenbases. Let's suppose that A acts on ket I'll call nr, brings out an eigenvalue an times ket nr. Now the r here is an index that we introduce to what we say resolved degeneracies. That is to say, nr, in the notation nr, we let r run up from 1 up to what I'll call d sub n, and d sub n is defined as the order of the degeneracy of the eigenvalue an. In other words, it's the dimension of the corresponding eigenspace. And so the idea is that these kets nr, the n indicates the eigenspace, and the r is a label of a orthonormal basis chosen inside that space. And as I mentioned, there's a great deal of arbitrariness in how you choose that basis. In any case, let's use this notation for the eigen. Notice the eigenvalue doesn't depend on r, it only depends on n. Well, if you have this, so this is just notation for the eigenkets, the orthonormal eigenbasis. Corresponding to this, we have a resolution of the identity that says that 1 is the sum on n and r of the outer product of nr with nr. This is just the normal thing you get when you write a resolution of identity in terms of an orthonormal basis. Turns out you can also write the operator A in terms of the orthonormal basis. It looks like this. It's the sum on n and r of the eigenvalue an times nr, outer product of nr. That's just like the line above, except you inserted the eigenvalues under the sum. How do I know these two operators are the same? Well, you see, if you have an operator and you know what it does to a set of basis vectors, then you know what it does to any vector because of linear superposition. So the way you prove that these two sides are equal is you allow them to act on a set of basis vectors. Well, what basis vectors should you choose? Well, the obvious answer is these basis vectors. You put those in there, and you can easily check that both sides give you the same answer. By the way, I should have mentioned something here, which is the orthonormality conditions of these vectors. These are the following. This is that nr scalar product with n prime r prime is chronometer delta n prime, chronometer delta r prime. The two chronometer deltas appear for different reasons. The reason it's orthogonal in n and n prime is because of the property over here that eigenspaces are orthogonal. Or in this picture here, if we belong to different eigenspaces, they're orthogonal. Whereas the orthogonality in r prime is because of our convention of choosing an orthonormal basis inside each of the eigenspaces. But in any case, this is the complete orthonormality relation, and that's what leads to this resolution of the identity and also this expansion of the operator A in terms of its eigenvalues and its eigenbasis. All right. Now, I defined the direct sum of two subspaces up here. I hope it's clear what that means. Let me just mention now that the completeness property can be expressed in terms of the direct sum. It says that if you take the direct sum of the eigenspaces, all of them, you will get the entire ket space. This is a statement of completeness in terms of direct sums. Just a way of saying it. All right. As I mentioned, most of the theorems about eigenvalues and eigenkets and so on are considerably simpler in finite dimensions. Let me say something now about infinite dimensional case, so you can get an idea of some of the things that can arise there. You can actually see some of it already. You get continuous spectrum in the infinite dimensional case. It is a possibility. In the finite dimensional case, it's always a finite spectrum. A discrete spectrum, I should say. To illustrate what can happen in infinite dimensions, Let's talk about the space of wave functions in one dimension, which you know a lot about already. And let's talk about the momentum operator, which I'll denote by P, which is, of course, minus IH bar ddx in the Schrodinger representation. And I'm going to put a hat over the momentum operator to distinguish the operator from the eigenvalue. So let's let P without a hat be the eigenvalue of the operator. So the eigenvalue eigenfunction problem for the momentum looks like this: is that P acts on some function. Let me call it u sub P of x, which is supposed to be an eigenfunction of the momentum operator with eigenvalue P. So when you let P act on it, it has to just multiply it by P. This is the defining equation. This is the eigenvalue eigenfunction equation. However, since the momentum operator is minus IH bar ddx, this becomes ddx of u_p of x, which is a simple differential equation. And when we solve it, we find that u_p of x is equal to e to the itx over h bar. And that's it. Okay, so within a multiplicative constant, that's the eigenfunction. Now, this differential equation has a solution for all values of the momentum eigenvalue, not only real ones, but also complex ones. There's a solution for any value of P. Does this mean that the spectrum of the momentum operator is the entire complex plane? Well, the answer is no, and part of the reason is that this is in the continuous spectrum, and I need to tell you some things about that. But let's just notice that if P had a non-zero imaginary part, if we're off in the so if we look at the eigenvalue plane, which is our real P imaginary P, if you imagine an eigenvalue which is off here in the complex plane with a non-zero imaginary part, then this function would diverge exponentially, either for positive x or for negative x, and it would be rather badly behaved. It certainly wouldn't obey the boundary conditions that you're used to in quantum mechanics, where you want wave functions to die off to infinity. Actually, what you really want is the wave function to be normalizable, because normalizable wave functions is what defines Hilbert space. Those are the wave functions that are physically meaningful, because the probability of finding a particle somewhere has to be 1, and so only normalizable wave functions are physically meaningful. Well, in any case, if P has a non-zero imaginary part, it's certainly not normalizable. What happens if P is real, sitting on the real axis? Well, then this becomes, the familiar sine and cosine, cosine x plus I cosine x. And so it's just a wave, which, however, does not die out as x goes to plus or minus infinity. In fact, its absolute value is 1 everywhere. So it's still not normalizable, and it still doesn't represent a physical state, and it still doesn't belong to Hilbert space. And so what we have to say is that if you're looking for normalizable vectors or normalizable states that belong to Hilbert space, the momentum operator doesn't have any eigenfunctions at all, not much less an eigenbasis. So how do we deal with this situation? Well, I'm just going to describe to you how one normally thinks about this. In the first place, we restrict consideration to just real values of the momentum. This, of course, is the idea follows the case of finite dimensions in which permission operators have any real eigenvalues. If we do that, then we can take this eigenfunction u_p of x and allow me to normalize it by dividing by the square root of 2 pi h bar, just a normalization constant. But the reason for doing that is that if I take the scalar product of up, let's say up prime, the idea here is to investigate the orthonormality relations of these eigenfunctions. Let's just abbreviate this, by the way, by writing it as pp prime and drop the u, where we just label the eigenfunction by its eigenvalue. Well, this is the same thing as the integral over x of up of x complex conjugated times up prime of x. That's equal to the integral over x divided by 2 pi h bar of e to the minus I p minus p prime x over h bar. Get my axis out of the way here. And that is the standard representation of the delta function p minus p prime. And so to summarize this in one spot, we have the scalar product of p prime is the Dirac delta function of p minus p prime. If we divide by this square root of 2 pi h bar is a normalization. That's why I did this, to make this delta function come out. So what we see is that these eigenfunctions of the continuous spectrum, that's what we're getting here, are normalized in the delta function sense instead of a Kronecker delta sense. Moreover, these eigenfunctions with p on the real axis are complete in a certain sense also. They're complete in the sense that an arbitrary wave function psi of x can be represented as a linear combination of these u of p's. However, since the eigenvalue p is a continuous variable now, we have to use an integral instead of a discrete sum. And so we write this as an integral over dp. Let's call it expansion coefficients. I'll call phi of p times up of x. That's the idea. We want to see is, do there exist expansion coefficients such that any psi of x can be represented this way? And the answer is yes, because if you write this out more explicitly, it becomes the integral dp over the square root of 2 pi h bar, phi of p, well, I'll put the up of x first, e to the ipx over h bar, and then phi p. And so what you recognize is that psi of x is the Fourier transform of phi of p. And so by Fourier's theorem, this has an inverse, which is integral dx over the square root of 2 pi h bar, e to the minus ipx over h bar times psi of x. And so the answer is the expansion coefficients exist. They're nothing but the Fourier transform of psi, or as we say in quantum mechanics, of the momentum space wave function. And in this sense, these eigenfunctions of the continuous spectrum are complete. All right. Now, that's the situation, part of the situation with the momentum operator in a continuous spectrum. I think I want to say one more thing here, which is to take this last formula here, and let's just reinterpret this. Notice that this becomes the integral over x, and if I take the 2 pi h bar and the e to the minus ipx part, that's the complex conjugate of our eigenfunction. So let me write this as up of x complex conjugated, multiplied times psi of x. And this, in the Dirac notation, is the scalar product of the basis function with psi, so I'll write it like this as p psi. And let me accumulate that in a single box, too, because that's interesting. It says that phi of p is the scalar product of p psi. And so the expansion coefficients, which we otherwise call a momentum space wave function, are just the components of the state vector psi with respect to the momentum basis. Let's do something similar with the position operator. Again, in one-dimensional wave mechanics. So let's call x hat as the position operator, which is multiplication by x. So the hat is the operator, the x is the number. By the way, as an aside here, put it over here somewhere, there's some terminology that goes back to Dirac, which I'll use occasionally in this course. Dirac distinguishes between what he calls a Q number and a C number, and you'll certainly hear this if you're in the quantum mechanics business very long. Well, a Q number is just Dirac's notation for a terminology for an operator. And a C number is a terminology for an ordinary number, that is to say, an ordinary complex number. I remember this because C stands for complex. But anyway, the distinction here is that x hat is the Q number and x is the C number here. All right, and let's let x of 0 be the eigenvalue. And let's let fx0 of x be the eigenfunction. So we want x hat acting on fx0 is equal to x0 times fx0 of x. Like this. However, since x hat just means multiplication by x, this is the same thing as x times xf0 of x. And if you put these together, this implies that x minus x0 times fx0 of x is equal to 0, which implies that either x equals x0 or else fx0 of x is equal to 0. this function must vanish everywhere except at x equals x0. It can only be non-zero at one point, is what this is saying. Well, the interpretation of this is that we interpret it this way by saying that f of x0 of x is the delta function of x minus x0. Delta function is not a real function, but it can be interpreted as a limit of real functions, and in some representations of it, you see this as looking like something that becomes concentrated at a point. If we take this definition of fx0 of x as the eigenfunctions of the position operator, then we can compute their scalar products. Let's examine the orthonormality conditions of them. Let's take the scalar product of fx0, fx1. This is the same thing. I'll just write this for simplicity by writing just down the eigenvalues instead of the full function, x0, x1. But this is the same thing as the integral over x of delta of x minus x0 complex conjugated times delta of x minus x1. Well, the delta function is real, so the star doesn't do anything. And if you do the integral, you get delta of x0 minus x1. Yes. So comparing to what we have up above, we have something similar in the x representation. The scalar product x0, x1 is a delta function of x0 minus x1. Also, there's other simple identities that we have. If we have psi of x, it can be written this way. It's the integral over, I guess I want psi of x0. It's the integral over dx of delta of x minus x0 times psi of x. This is one of the properties of the delta function. But this can be also written as the integral over dx of fx0 of x complex conjugated times psi of x, which is therefore the scalar product of x0 with psi. And so we find that the wave function, psi of x0, is the scalar product of x0 with psi. And I ask you to compare these two results with the momentum results up above. You see in both cases the wave function is in effect just the expansion coefficients of the abstract state with respect to the basis, which is an eigenbasis of an operator. This is one reason for not regarding wave functions in configuration space as being the central object of the whole story. Rather, it's the abstract vector is really the central object. And these are just different choices of components by different choice of basis. Choice of basis is an arbitrary choice. All right. Now, there's finally a couple more relations that are related to this, which I'll skip over the details and just summarize the results. These are resolutions of the identity, which apply both in momentum and in the case of position. It looks like this is that you get 1 as the integral over p of the outer product of pp. And you also get 1 is the integral over position dx of the outer product of x with x. And these become the resolution of the identity relations in the case of the continuous spectrum. Here's another couple of remarks about the continuous spectrum. If we have a single value of p, let's speak of momentum. Let's take a single value of p on the momentum axis here. Single value of p, here's the real part of p, and here's the imaginary part of p. So some point in the spectrum of p. Can we talk about the eigenspace corresponding to that momentum value? We could certainly do that in the case of the discrete spectrum. And the answer is no, because the eigenvector corresponding to this particular eigenvalue doesn't even belong to Hilbert space. These resolutions of the identity we have here work in the function sense, but the vectors in question don't lie in Hilbert space. This is the difference between the continuous spectrum and the discrete spectrum. And there is no subspace of the Hilbert space corresponding to a single value of momentum. On the other hand, if I want to take two values of momentum, let's say P0 and P1, or let's make it P1 and P2, and consider the interval. Let's take the interval I to be equal to the interval from P0 to P1. Then it does make sense to talk about the subspace corresponding to that interval. And later on, I'll write down an explicit formula for this. But I think you can believe this on the basis of what you know about signal analysis. You know about band-limited signals, or filters in electronics that remove all the frequencies except outside a certain frequency range. Well, imagine you have such a thing here, and I'll draw there as the acceptance of some kind of a filter that accepts wavelengths that lie, or momentum that lie between P1 and P2 and reject everything else. That's actually a projection operator that projects you onto a subspace corresponding to a band in the continuous spectrum. So in the continuous spectrum, you get subspaces of the Hilbert space corresponding to intervals of the continuous spectrum. Let me say something about the resolution of the identity in the case of the continuous spectrum. It might be easiest if I just do an example, which is hydrogen atom. Let's let as usual in hydrogen atom language, let's let NLM be the wave functions of the bound state wave functions of the hydrogen atom. These are orthonormal in the sense that NLM scalar product with n prime, l prime, m prime. This particle deltas in n prime, l prime, and m prime. But the energy eigenvalue only depends on n. Hamiltonian acts on this and gives us En times NLM, where I think you know that En is proportional to -1 over 2n squared. But the point is it depends only on n and not on the two other quantum numbers. And this means that the eigenspaces of the hydrogen atom Hamiltonian are degenerate, and the L and the M correspond to the R index, which is still there. I guess it's gone now. The R index I introduced earlier that just indicates, in effect, an arbitrary choice of an orthonormal basis in each of the energy eigenspaces. However, the hydrogen atom also has positive energy eigenstates, and I'll denote those like ELM like this. And this is the case where E is greater than or equal to 0. It's a continuous spectrum now. There's no discrete values of the energy. And we can normalize these in the following way, is that E in ELM, scalar product with E prime, L prime, M prime, is a Dirac delta function in the energies times the Kronecker delta in the L's and the Kronecker delta in the M's. And if you do this, then, so these are the orthonormality relations. Actually, they're part of them. Here's the orthonormality relations for the bound states. Here's for the unbound states. There's another one, too, is that the scalar product of a bound state with any unbound state is 0. The bound states and unbound states are orthogonal. So, in three formulas here, these are the orthonormality relations. Now, here is the resolution of the identity for the hydrogen atom. We have the sum on NLM, which runs over all the bound states of the outer product NLM, NLM. And then we need an integral from 0 to infinity over energy. And then the sum on L and M of ELM, outer product of ELM. This is what it looks like. There's also, you'll recall I also mentioned that the operator itself can be written in terms of its eigenstates. If we do this for the hydrogen atom Hamiltonian, it looks like this. All we have to do is put in the energy eigenvalues under the sum for the bound states, and also for the unbound states. We put in an E here. Like this. This is what it looks like in the case of the hydrogen atom. Okay. Now, an important theorem regarding observables in quantum mechanics is that two observabilism theorem. I'll write it out. Observables A and B possess a simultaneous eigenbasis if and only if they commute. It's an important theorem for quantum mechanics because the question of commuting observables is closely related to the question of the possibility of making simultaneous measurements on two different observables without one measurement interfering with the other. It's related to the uncertainty principle and things of that sort. So the theorem says that observables A and B possess a simultaneous eigenbasis if and only if they commute. Now, an eigenbasis, as I mentioned earlier, is a basis which is also consists of eigenvectors of or eigenkets of a given operator. When I mean a simultaneous eigenbasis is I mean a basis that's eigenkets of both operators A and B simultaneously. So every eigenvector is an eigenvector of both A and B. How do we see that this is true? Probably the easiest way is to go back to this picture of the orthogonal eigenspaces. And I'll draw one that's two-dimensional and one that's one-dimensional. So let's call this En here. And here's a different one, call it Em. I'm mainly going to concentrate on En. So here's the idea. Let's suppose that I have A acting on a ket U gives me A sub n U. That means that ket U lies inside this eigenspace En. And it means that when A acts on it, all it does is it multiplies it by a complex number, so it gets longer or shorter, maybe it changes its direction, but it stays inside En. All right. Now, what about if we let the operator B act on a vector that lies in this space En? What can we say about that? Well, let me put parentheses around that. So, in particular, B is going to act on this vector. What will it do? Could it possibly lift it out so that it sticks out of the space somehow? That's the question. The answer is no, because if I take BU and I let A act on the left-hand side, this is, of course, the same thing as AB acting on U. But because B and A are assumed to commute, that's the same thing as BA acting on U. And then the A acts on U and brings out the eigenvalue AN, which is just a number. So this can be written as AN times B acting on U. And the result of this is that the vector BU, you see, is an eigenvector of A with the eigenvalue AN. That means it belongs to the space En, and so this picture I drew is wrong. Instead, BU has to be some vector that's also inside this space. So this is an example of what we call an invariant subspace. We say that the eigenspace of the operator A is an invariant subspace of the operator B, because B acts on any vector in this space and maps it into another vector in the same space. This space is also an invariant subspace of A because A acts on any vector in this space and just multiplies it by a scale factor, which certainly keeps it in this space. So the eigenspace of A is actually an invariant subspace of both operators if they commute. Now, if you have an invariant subspace of an operator, you can define what's called a restriction of the operator to the subspace. It just means you ignore the rest of the space and you just look at the subspace. If an operator if the subspace is not invariant under the operator, then it doesn't make any sense to talk about a restriction, because if I've got a vector in a subspace and I let an operator act on it and brings it out of the space, then it doesn't make any sense to say what is A restricted to the space. But anyway, we do have an invariant subspace here of both A and B. Let's call the restrictions of these. Let's put a bar over this to indicate the restrictions of the operators, both these operators of this subspace. The operator A is actually quite easy. It's just the eigenvalue multiplied times the identity and restricted to this space. The operator B is not so simple to write, but one thing we can say about it is that it's Hermitian. And so the result is that B, being Hermitian on this subspace, possesses an orthonormal basis on this space. So there's a B basis here, which is orthonormal. And that B basis is obviously an eigenbasis of A as well, and therefore you get simultaneous eigenbasis of the two operators. Okay. Well, that's all I'm going to do for today. To remind you again, we meet next time in 325 LeConte, not here. This room's being taken over. It's obvious from the eigenvalue equation, however, that if you multiply u by any constant, complex constant, you get another eigenket. So this equation does not uniquely determine the eigenket, only to within a multiplicative constant. Or to say it another way, if I take this non-zero ket u and I multiply it by any factor I want, it could be a negative factor as well. And since these are complex vector spaces, it could be really complex numbers, including phases and so on. But in any case, the result is what you get is, from a given non-zero ket, you can construct a whole one-dimensional subspace of eigenkets. You could call this an eigenray if you want. In some sense, this equation really determines an eigenray rather than a single eigenvector. Now, it may happen that there is, in addition to this vector u, this ket u, it may happen that there's another vector, or ket, which is linearly independent of the first one, which is also an eigenket with the same eigenvalue. Let's call this b, let's say. ab is equal to lowercase ab. The point is the a's here are the same, but the b's here are different. And let's suppose the b is linearly independent of u, so that it sticks off in some direction like this. Here's the b. Then it becomes apparent that any linear combination of the u and the b is also an eigenket. And so the space of eigenkets, you see, becomes a two-dimensional vector space like this. Under these circumstances, it becomes appropriate to speak of an eigenspace. And that's what we'll do. We'll call this the eigenspace. I'll call this E sub A, script E sub A. I'm generally using the notation script E here for the entire ket space, the entire vector space. So with an A subscript on it, it stands for the eigenspace corresponding to eigenvalue A of a given operator A like this. And the result of this is that we get a geometrical interpretation of this eigenvalue-eigenket problem, which is that if you have an operator A, it corresponds to certain privileged subspaces of the ket space. In general, we can think of the two different forms, rather easily equivalent. And I just want to mention a very simple but important theorem that occurs in quantum mechanics, which is that if you have two Hermitian operators, then the product of those Hermitian operators is Hermitian if and only if they commute. Proof is so trivial that I won't go over it in class, but it is something that will occur many times in the course. Now, what I'd like to start addressing today, first of all, is the subject of eigenvectors and eigenvalues, or eigenkets and eigenvalues. Let's suppose we have an operator A, not necessarily Hermitian, acting on some ket space, and we have some non-zero ket u, take it to be non-zero, such that when you let A act on u, it just multiplies u by a number, lowercase a, which in general is a complex number. Here, capital A is the operator, and lowercase a is what we call the eigenvalue, as I guess you all know. And likewise, the ket u here, we'll call this the eigenket. Or sometimes eigenfunctions if we're talking about wave functions, or eigenvectors. Anyway, that's the eigenket and the eigenvalue. The eigenvalue, as I mentioned, in general is a complex number. It depends on the operator A. Now, the situation regarding, or the theory regarding eigenvalues and eigenkets is considerably simpler in a finite dimensional ket space than it is in an infinite dimensional one. So I'm going to begin by telling you about finite dimensional spaces, but I'll make a few comments as we go along about how the situation is different in infinite dimensions. Here's the first thing to notice is that if you have a ket u, an eigenket, now it's supposed to be non-zero because if it were equal to 0, this equation just says 0 equals 0, and it's not very interesting. So we exclude the 0 case. So if U is a non-zero ket, then you can think of it as a vector that sticks off somewhere like this in the space in question. Here's the vector U, or the ket U. It's
Oh, that's
I'm actually not. Looking out stuff.
Oh, really?
I use the vector field.
I know, me too.
You can take it from down the road, it's fired from after all.
I want to call your attention to the fact that we have to leave this room because it's too big and bigger classes needed. So effective next lecture, which is on Wednesday, September 1st, we'll be moving to 325 LeConte. So please don't forget that. All right, last time I was telling you about Hermitian operators. I reviewed here the definition of a Hermitian operator, which actually give us the complex plane for the eigenvalue. Then in general, the spectrum, and I mentioned a moment ago that I'm describing the situation in a finite number of dimensions, first for simplicity. And if we're in a finite number of dimensions, the spectrum consists of a discrete set of points which can be distributed here and there in a complex plane. That's the spectrum of the operator. All right, that's just some terminology mostly. Let me give you some examples of spectra of operators coming from quantum mechanics. Let's first of all talk about the harmonic oscillator Hamiltonian. The harmonic oscillator Hamiltonian. So let's write H x on UN gives us E n UN. And as you all know, the energy eigenvalues are equal to n plus a half h bar omega. And so the spectrum, we have to look in the complex energy plane. There's real energy, imaginary energy. The spectrum consists of points first 1/2, then 3/2, 5/2, 7/2, and so on. As you see, it's a discrete spectrum, and it's on the real axis. Here's another example. Let's take the free particle, h equals p squared over 2m. And then here's what the spectrum looks like. Real energy, imaginary energy. In this case, there are eigenfunctions for all non-negative values of the energy. So the spectrum consists of the entire real axis like this. Try to draw it heavy. The entire positive real axis, not negative. This is an example of what's called a continuous spectrum because it's not discrete points. Continuous spectrum only arises in infinite dimensions, and I'll say more about it a little later, but right now I'm just giving you a preview of some of the things that can happen. Here's another example. Let's take the hydrogen atom, Hamiltonian. Again, we talk about the energy spectrum. If I think of two of them, just try to draw a picture of it. If I've got two spaces, here might be one, and then here might be another one going off like this. I've drawn one of them to be two-dimensional, one to be one-dimensional. Let's say this is E1 and this is E2, are two different ket spaces corresponding to eigenvalues A1 and A2. You can imagine it looking something like that. All right. Now, as you probably know, if there is more than one linearly independent eigenket, then we say that there's a degeneracy. And the number of linearly independent eigenkets that correspond to a given eigenvalue is something we'll call the order of the degeneracy. So the way I drew it here, the order is 2 because it spans a two-dimensional subspace. The order of the degeneracy is just the dimension of the eigenspace. If the eigenspace is one-dimensional, like I drew here for this E2, then we say it's non-degenerate, which means that it doesn't mean the eigenket is unique, but it's unique to within a single multiplicative constant. All right, so as we'll say here, the dimensionality of the eigenspace En is what we'll call the order of the degeneracy. So the order of the degeneracy is always 1, but it could be greater than 1. All right. Now, another thing that comes out of this is that given operator A is associated with a collection of numbers, generally complex numbers, which are the possible eigenvalues of A. That's got a terminology. It's called the spectrum of the operator A. So the spectrum of A is just the set of eigenvalues A n of A. That's all it is. This is the spectrum of our operator A. And it's usually viewed as being a subset of the complex plane. So it's a complex eigenvalue plane, really. So if I have the real A and imaginary part of A as being the